Hi everyone, in this video we'll dig a little deeper into some of the amazing properties of planets and moons in our solar system. In order to understand these properties, we have to start on Earth with an understanding of the tides. Because our planet is covered with water, it's particularly visible to us when that water sloshes back and forth in response to the gravitational influence of the moon. And the length of these arrows represent the magnitude of that gravitational force exerted by the moon on the part of the planet. So here, for example, the gravitational force is the biggest. The water sloshes toward the moon, and this point on the Earth experiences a high tide. The Earth itself is being pulled toward the moon, and it leaves this water behind on the opposite side of the Earth from the moon. So this water kind of gets left behind, and this side of the Earth experiences a high tide as well. If you start out where the red star is on this picture, then 6 hours later, the Earth has rotated. So the red star is now in this position, facing 90 degrees away from the Earth-Moon line. And 12 hours later, it's in this position on the opposite side of the Earth from the moon, again experiencing a high tide. And finally, we move to here, and after an entire day, we get back to the place where we experienced our original high tide. So based on this, how often does a given region on Earth experience a high tide and a low tide? Well, you can see, since we're rotating rather once per day, we're going to be facing the moon and facing away from the moon once each in 24 hours, and therefore we'll have 2 high tides per 24-hour period. You might wonder what the influence of the sun is in all this. The sun is much more massive than the moon, and that alone would lead you to predict a greater gravitational influence on the Earth from the sun than from the moon. However, the sun is also much, much farther away, and gravity, as we know, goes as an inverse square law. So the fact that it's so much farther away and the denominator of that expression for gravitational force is so much bigger causes the gravitational influence of the sun to be less on the tides. Nevertheless, it does still influence the tides. So we have spring tides when the sun and the moon are in line. They're both pulling in the same direction on the Earth. They're both causing a high tide because of their positions on the Earth. We call these spring tides, even though they need not occur in spring. And by the same token, the neap tides happen when the sun and the Earth line is 90 degrees away from the Earth-Moon line. So the influence of the moon is bigger, but the influence of the sun is enough to either augment or offset that influence a little bit, depending on the relative geometry of these bodies. Tidal locking happens because the Earth rotates much faster than the moon revolves around the Earth. And because of this, the water, it takes some time for the water to, for the big bulge to reorient toward the moon. The moon is actually dragging the bulge back from its position. So the bulge precedes that direction of motion of the moon by a little bit. This drags back the rotation of the Earth. It makes it rotate slower. And over many millions of years, the day length of the Earth is actually increasing. Many millions of years ago, the day was a few hours shorter because of this effect. And over time, the Earth will become tidally locked with the moon. The moon is already tidally locked with the Earth because the Earth's mass is so much bigger. So the moon rotates one time every time it goes around the Earth. And because of that, it always presents the same face to the Earth. And Mercury, for example, is almost tidally locked to the sun because Mercury's orbit is very elliptical and it moves much faster at some points in its orbit and much slower at other points of its orbit. Its rotation is more complicated, but and so it actually rotates twice for every time it revolves, but it's kind of almost tidally locked. And most of the moons in our solar system are already tidally locked to their planets. And you can see there's this bulge, this kind of permanent tidal bulge, because the influence of the Earth's gravity is greater on one side of the moon than it is on the other side. So it's more like a melon than a sphere. Of course, this diagram is much exaggerated. So what causes a planet to have a moon, and what would cause it to have rings like Saturn? Now, moons are pretty big. So as you get closer to the planet and gravity gets bigger, the gravity on the part of the moon that's closest to the planet exceeds the gravity that's on the part of the moon farthest away from the planet. And this effect wouldn't be noticeable except that the moons are big enough for it to be noticeable. So it's not a factor for like small spacecraft or even for very small moons. But if the moon has about the same density as its parent planet, then about 2.5 times the radius of the planet away is the minimum distance that the moon can continue to exist as a moon. If it gets inside that distance, then it starts getting broken up. And the objects that make up the broken up moon will rotate at different rates. So here I have my paper plate, and you can see I drew some stars in different colors on it. And if I make my paper plate rotate, all of the stars stay in a line. They rotate together. But for rings around a planet, Kepler's laws tells us that this isn't going to happen. The parts closer in, that red star that's closer to the center of my paper plate, will have a shorter period than stars that are farther up. So it's going to go faster. It's not going to rotate with the same period as all the other stars on the plate. And that's true of the planets in the solar system. Mercury, for example, has a much shorter period than planets farther out, etc., etc. So that's what happens to the moons. They break up and those inner parts start going faster relative to the outer parts. And it's thought Mars might once have had a ring. Scientists have noted that one of its moons, it has two moons, Phobos and Deimos, and Phobos keeps getting closer to the planet. Again, not at any sort of fast rate, but in a rate such that it's thought that millions of years ago, it might once have been a ring that kind of clumped up, the objects in the ring clumped up, much like solar system formation that we've studied before, and formed this moon. And then the moon gets kind of inside the Roche limit. They think this cycle has been going on again and again. And every time it happens, the new moon that's formed is smaller than the old moon that used to be there. And the rest of the debris rained down on the planet. It would explain some of these sediment deposits that have been found right around Mars's equator, right underneath where the moons revolve. Speculative, but it might have been, and it might happen again in several million years. So planets can have rings or moons, and it sort of depends on where things end up when the planets form. The other thing that's important to understand about planets and moons in our solar system is their atmospheres. We've said already that having a high mass helps a planet retain an atmosphere. That's why, for example, we said the Earth has an atmosphere and the moon does not. It's just the moon is smaller. It can't hold on to an atmosphere. That's not the entire story, though. Strong magnetic fields help hold on to atmospheres, and cold temperatures, because at cold temperatures, the molecules in the atmosphere are moving more slowly. So they can't escape from the atmosphere as easily. They need to achieve escape velocity to get out of the influence of the planet's gravity, and at cold temperatures, they're just not moving fast enough. Also, if they're very dense, then they'll stay closer in to the planet. And also, if the planet can replace its atmosphere, like if it has volcanoes, for example, that spew gas out of them, then, or plate tectonics or geologic activity, then the atmosphere can get replenished, and that will also help a planet or moon retain its atmosphere. So there are a lot of factors. For example, Venus has a smaller mass than the Earth, but it has quite an impressive atmosphere, as we'll see. Titan, this moon of Saturn that's pictured on this page, has quite a big atmosphere. It also has a smaller mass than the Earth, even though its mass is really impressive. It's a really big moon. And it also has lakes of liquid methane on its surface, which is really cool. One of the only moons that has been seen to have liquid actually on its surface. So Titan's really cold. It has that going for it. It's off near Saturn, so the gas, it's harder for that atmosphere to escape. So that's something that we need to understand about any planet or moon that we're looking into in our solar system as well. Venus, I mentioned, has this greenhouse effect going on. And the greenhouse effect is critical for life on Earth. Without it, the Earth would be a solid block of frozen ice. It happens because the atmosphere is transparent to visible light, meaning that the visible light can get through as long as there are no clouds in the way. And then it gets absorbed by stuff on Earth, heats that stuff up, and the stuff re-radiates that energy as infrared radiation. But the infrared radiation is blocked. It can't all make it out into space, and the atmosphere causes it to be trapped near the Earth like a warm blanket. That blanket's getting a little too warm on Earth, and we're all very worried about that. But on Venus, it's gone beyond the point of being worried about it. Venus is, in fact, hell. It has a runaway greenhouse. Its atmosphere is composed of carbon dioxide, a very potent greenhouse gas, which traps heat inside it. Its surface temperature is hot enough to melt lead. And the pressure down on the surface of Venus is 90 times air pressure at sea level, so it's like being underneath a kilometer of water. It wouldn't be good to be on Venus. It in fact rains sulfuric acid on Venus, but the sulfuric acid, of course, evaporates before it hits the ground because it's so hot. So this Venus sounds like not a very nice place to go and live, but let's colonize it. Let's go there. Because if we just didn't limit ourselves to thinking about going down to the surface, we could actually get an incredibly Earth-like environment about 50 kilometers up. The air pressure 50 kilometers up on top of the surface is very similar to the air pressure on Earth. The gravity is like 0.9 G. It's very similar to Earth gravity. So there's all these concerns about bone decalcification. Going to Mars, for example, where the gravity is so much less, wouldn't be an issue on Venus. Well, that wouldn't anyway. There'd be some other problems. But Venus is closer to us, so we could get there a little bit easier. And if the pressure is right and the temperature is right, the air isn't breathable, but breathable air could be in our balloons, and we could have these cloud cities, and the air that makes up the balloons could be breathable. Nitrogen and oxygen would be just buoyant enough to keep us at just the right altitude above the surface. And as an extra bonus, we'd be shielded from cosmic radiation, another big concern about going to Mars, by the rest of the atmosphere on top of us. Now, I don't know if I'd sign up to go to one of these cloud cities, because I'd worry a lot about who was in charge and whether they would maybe decide that if you didn't do what they wanted you to do, they'd push you out, because then you'd be headed straight for hell, literally and figuratively, by plummeting down onto that horrible Venusian surface, because underneath those beautiful shimmering white clouds is not stuff, not a place that anyone would want to go from Earth. But nevertheless, it's a thought. It's a thought. Don't leave Venus out when you think about colonizing other parts of the solar system. Thanks for watching.